Hello, lab partner. All right. Now, in order to explain how you're going to do your calculations, I'm going to draw a picture. Pictures are worth 1,731 words. Yes, they are. I know you've heard the saying, a picture is worth 1,000 words. Nope, not 1,000. 1,731. I've actually counted. I've actually done the research. And the person who made that saying up got lazy and quit. I didn't quit. Okay, 1,731 words. So I'm going to draw a picture so you can help you understand how to do these calculations and where the numbers are going to come from. We've actually explained a couple of them, but let's see if we can draw a picture. And if you're still confused on why I got this number for this or this, let's see, here's how it goes. So I took an ice cube out of the freezer, which is -6 degrees Celsius. I checked that, but we're not going to use that number. Because if you've watched the video on a heat of fusion calculation, when I used an ice block coming out of the freezer, I actually incorporated that into the calculations. Not going to do that here. Well, why not? Why not? Because remember, I left that ice cube out for a little while. Yes, I did. I left that out and bantered while we were doing other things and let that ice cube acclimate to its melting point. It was getting a little slick on the outside because it was beginning to melt. So our ice had been out for just, it doesn't take very long, just for a few minutes, we got that ice already to its melting temperature. So I'm going to draw the ice at its melting temperature. So here's my ice cube, it's 0 degrees Celsius. Then what happens to it? You put it in the water, it begins to melt. So the ice melts and becomes water at 0 degrees Celsius. Cold water. That's the source of your cold water, was the melted ice. Then we had a bunch of hot water. Okay, this is the hot water, and this actually is our cold water. And the hot water was at a particular temperature. For the first trial, it was at 43.4 degrees. It was at 43.4 degrees Celsius. Now what happened? Well, the water started getting cold. It started getting warmer. Colder, because I'm a mess. I am a mess, people. I mean, if you wear a shirt like this, you know that person's a mess. This water started getting colder. This water, cold water, started getting warmer. Because, of course, the cold water is going to bring the temperature of this down, but the temperature of this is going to bring the temperature of that up. And then they met at some point eventually, and that's what I was calling the equilibrium or final temperature. They both mixed, and finally we got this final temperature that the two, hot and cold, settled on. Now that equilibrium temperature for the first trial, that final temperature for the first trial, was temperature of hot water after ice is melted is 18.5. So the temperature of the hot water drops to 18.5 degrees Celsius as the temperature of the cold water went up to that temperature, and that's where it settled on for a good amount of time before finally this started to increase slowly as the room temperature, hot room temperature, was adding temperature to the cooler water. All right, so this is where we get those numbers from. So let's go through it one more time. The temperature difference of the hot water was the 43.4 minus this, because this is the final temperature. I call it TF, the final temperature of both the hot water and the cold water. So subtract those two. That's what we did. We subtracted those two, and we came out with a difference of 24.9. And then we subtracted these two and got a difference of the cold water, which is just, of course, you're subtracting 0, so it's just the 18.5. So 18.5 degrees. And this is where we got our numbers. Now, we also got the numbers for the mass of the ice. The block was 24.1 grams, the ice cube. 24.1 grams, because that was the total amount of water after the ice melted. We got that number, and that was the second to the bottom number. That was the total amount of water. It was 123.4. Well, 24.1 of it came from the melted ice. All right, so this is a drawing which is going to help us do the calculations. You go through the calculations, each one by one. So I will kind of give you an idea of what you're doing with your calculations. I'm not going to do them out. And notice I didn't show you my data table for the second trial, all that you have to do on your own, lab partner. Yes, you do. Yes, you do. You got to do some work there, lab partner. So you figure out the rest of those numbers for trial 2. And what I want you to do is do a calculation for each trial. There's 5 of them, 6 of them, A through F for each trial. And I want you to show me the work for each calculation for each trial. All right, now, you have to use the heat equation to do calculations A and B, or 1 and 2, however you want to say it. Calculations A and B are done using the heat equation. Q equals M delta T Cp. Heat equation. All right, now, for A, you're doing a calculation for the heat that was lost by the hot water. Make sure you're using hot water data. Hot water data. Hot water. You need the mass of the hot water. Okay, remember the volume of the hot water was the mass of the hot water. So it was like 99 point something. Okay, so Q goes, I'll put this in for you here. 99.3 milliliters or 99.3 grams. The change in temperature of the hot water. That's the change in temperature of hot water. Make sure you're putting hot water data in. 24.9. Specific heat capacity is, for water, 4.1. I rounded to 4.19. You might want to use 4.186 if you're feeling a little bit more accurate. And okay, go ahead, use 4.186. But I use 4.19. 4.19. And you multiply that out, and you'll get the heat that was lost by that hot water. Just kind of looking at it, it's like 100 times 2,400 times 4. It's going to be like 10,000. So it's going to be somewhere around 10,000 when you do that out. Okay, B says calculate the heat gained by the cold water. So I'm going to use the same equation, but I'm not going to use hot water data. I'm going to use cold water data. Heat gained by the cold water. Well, I need the mass of the cold water. What was the mass of the cold water? That came from the ice cube, 24.1. Then I need the change in temperature of the cold water. Change in temperature of the cold water, 18.5 for the first trial. Okay, and then it's water, so we still have the same specific heat capacity, 4.19. And you multiply that out and see what you get. Let's see, that's 25 times, that'd be the 2,400 is a little less than that, times 4. So you want a little under 2,000 or something like that. All right, so like 2,000 or something. No, 1,000 something. Anyways, you multiply it out, get a number for it. Okay, you go ahead and you do that, and then it'll be calculation part B. Calculation C. This is the interesting one that messes you up. Gonna mess you up, Mr. T, Rocky 3, okay? Saying that to, Rocky, I'm gonna mess you up. And he did for a while there, but it's Rocky, so eventually Rocky won. Come on, it's Rocky. Where was I? Oh, yeah, part C. Okay, calculation C is asking you to calculate the amount of heat that was absorbed during the melting process. This is the one that always will get students. If I don't explain this, a lot of you will have a lot of problems. What the heck is that talking about? Okay, look at part A. You got a big number. This is around 10,000. Look at part B. Got a smaller number, between 1 and 2,000. Well, where did the other 8,000-ish joules of energy go? Because remember, energy can't be created or destroyed, it only changes form. So where did the energy come from to melt the ice? Where did the energy come from to melt this ice? Why did it melt? Hot water. Hot water provided the energy to melt that ice. Okay? Yeah. When the ice melted, it became cold water. But it didn't stay as cold water, did it? The temperature of the cold water went up. Why did the temperature of the cold water go up? Where did the energy for that come from? Hot water. Again, hot water. So the hot water had 2 jobs. Okay? Two jobs. It first melted the ice, then it caused the temperature of the cold water to increase. Now what we've calculated is the amount of energy that the hot water lost. In other words, the amount of energy that the hot water needed to do both jobs. Then for part B, we calculated how much of this energy that was lost by the hot water got put into raising the temperature of the cold water. So how are we going to determine how much heat energy went into melting that ice? Oh, we're going to have to use the heat of fusion equation. And no. This did two jobs. Melted ice, increased temperature of water. We determined how much we have here, 10,000. We determined how much went into this, went into raising the temperature of the cold water, 2,000-ish. Well, where did the other 8,000 go? It went into melting the ice, didn't it? So how are we going to figure out part C? How much energy went into melting the ice? Subtract those two. Take A and subtract B. Subtract them. And you'll get how much energy went into melting the ice. Now, that would give you the amount of energy it took to melt the ice. But the heat of fusion is defined as the amount of heat it takes to melt a gram of ice. So we had that number. When you subtract these two numbers, A and B, and you get the answer for C, that was the total amount of energy to melt all the ice. So how do we get the amount of energy to melt 1 gram? Divide. So for part D, you're going to take the answer for part C and divide it by the mass of the ice. So that'll give you the joules per gram of the ice. So you'll take that number and divide it by 24.1 grams, and that will give you the heat of fusion. All right, now I do ask you for part E to convert your heat of fusion from joules per gram, because that's what you're going to get. You'll get joules per gram, into calories per gram, just to do a joule to gram, joule to calorie conversion, that's all. So what you're going to do is you're going to convert joules to grams. Now here's the kicker. Here's what you need. That it takes 4.19 joules of energy to equal 1 small science calorie. And it takes 1,000 of those to equal a food calorie. So that's a small unit, which means it takes more of these to equal a small unit. That's a real small unit. Okay, the joule's small. So just convert. I want you to just convert the joules per gram to calories per gram. Use that conversion, do the math, determine how many calories that is. It should be a smaller number than what you got for part D. And last, for part E, no, that was part E, sorry. Last, for part F, do a percent error. Now, we all remember percent error. Okay, if you don't, oh, I didn't put it on the front. I usually will. I'll put the equations on the front for you. I didn't do that. That's okay. We'll put it down the board for you. So to get percent error, if you don't remember, we take the true value and subtract the experimental value. Then we divide by the true value, take an absolute value, meaning if you get a negative up here, you ignore it. And then to get anything into a percent, you multiply by 100. That's how we get our percent error. Now, sometimes the true value is called the theoretical value or the actual value. Either one of those three words work, but the experimental one is called the experimental value, what you get in the experiment. So whatever you get for an answer for both trials, trial 1 and trial 2, we're going to do 2 sets of calculations. So for trial 1 calculations, take that final answer that you got for part D. Let's do for part D, joules per gram. D, joules per gram. Put it here. And then use the true value. True value. What's true value? Come on. We went over this in our video. What's the true value for the heat of fusion of ice? Okay, in joules per gram. Okay, I'm not going to, no, you're going to have to go find it. Go look. If not, Google it, okay? Take the true value in joules per gram for the heat of fusion of ice, put it here and put it here. Subtract. If you get a negative, ignore it. And then you do a percent error. Do the same set of calculations for both trials. Okay, you know, you're a good lab partner. I like to see under 10% error on this lab. Sometimes we don't. Sometimes some students will get under 20%. That's okay. It's not too bad. But there are some reasons why we're going to get experimental error. You saw some of them potentially. I mean, you know, you might be making notes when you're watching me do it. You know, that can cause a little error here. And those little errors could build up. But I'm predicting you and I are pretty good lab partner. I'm predicting we get under 10%. If you get anywhere, you know, 3, 4, 5, 6%, that's good. That's good. And there are going to be errors. There's nothing you can do about a few things with these lab designs and for the the calorimeters that we use. Oh, by the way, it's going to be interesting. I want you to make a note. Make a note. We used the styrofoam cup, cheap, well, inexpensive. Don't say cheap. I don't like that. And we also used a more expensive calorimeter. Which one came out better? Were there any statistical difference? Statistical difference meaning is, you know, was it like 5% difference between the two? If not, yeah, you know. That's why I usually tell my students, just use the styrofoam cups, because they usually come out to be pretty darn close to the other one. So, but you do the calculations, see what you come up with your percent errors, and hopefully, I'm feeling good about us, lab partner. We're good. We did under 10%, and we're not going to get zero. Not on this one. No, no, no. Not even 1 or 2% probably, because that's really hard. There's just intrinsic errors to the lab, and with the calorimeters. There's nothing you can do about a little bit of error. But again, we're good. We're good, you and I. Okay? Good. So I feel good. I think that's it. What I want you to do for the write-up is you go ahead and give me the data table filled out and done. Show me your calculations, 1, 2, 3, 4, 5, 6 for each trial. That's 12 calculations altogether. And then answer these questions. I want you to answer these questions. I will not help you with these questions. I will not. So if you go, I don't know, what is this okay for question 1? I'm going to go, nope, sorry, you're on your own. You have to do some Googleizing, look them up, struggle through them if you have to. But those questions are for you to answer. All right, that's it. Have that lab done. Get it in the following week, and it'll be on time. And that was a great first experience, lab partner. I hope you had fun as much as I did. Until next time.